Hello and welcome to the September Wednesday webinar from the IEA Clean Coal Center. My name is Benedicta Brox and I'm the Communications Officer here. Our monthly webinars are available from our website, live or at any time on demand. Our reports are available for download for residents of member countries and employees of sponsoring organizations at no charge after one-off registration. The subject for today's webinar is Review of Flexible Operation of Coal-Fired Power Plants by Debo Adams. There you go, Debo.
Good morning, everyone, and thank you, Benedicta, for the introduction. So yes, as she said, my presentation today is a review of the flexible operation of coal-fired power plants. So this webinar is based on a presentation by my colleague, Dr. Colin Henderson, that he made at ESCOM earlier this month. So the installation of renewable energy power plants means that there will be an increasing need for fossil-fired plants to operate flexibly to balance the fluctuations in power from these sources. Today, I'm going to describe the means available for achieving high flexibility in coal-fired plants. Operating at widely variable output increases the wear and tear on equipment and reduces efficiency. However, the necessary flexibility can be achieved with acceptable impacts on component life, efficiency, and emissions. I'm also going to discuss enabling flexibility of other coal plants, such as CO2 capture plants. So, what do we basically need for the future as well as existing plants? This is the boiler at Isogo Unit 1 in the picture in Japan. There is a surprising variation in the reported ramp rates of existing plants, perhaps because of a desire to limit plant wear. Values appear to be around 2 to 5% per minute. They're generally more for some newer designs. Of course, the short-term response of a steam turbine for frequency control can be 10% per minute or faster. Renewables often do not provide frequency control, so the grid will need even more support from the fossil plants than currently. As you can see in this slide, it's a simplified diagram of a pulverized coal power plant. In the following slides, I'll go through the various main process areas in discussing how flexible they are and how to increase this flexibility. So basically, everywhere is involved. But the good news is that new systems can increase flexibility and reduce these adverse impacts and costs. Of course, things have to work together. There's no use being able to operate the boiler steam systems down to 20% if the combustion system cannot safely reach those conditions. Actually, if the minimum load only needs to drop to 30% of MCR, maximum continuous rating, experience has shown that even older plants can usually cope pretty well with this, provided the ramp rate is not pushed too hard. The costliest operations are startups and shutdowns, especially cold starts, so these are best avoided if possible. A way to reduce the number of damaging, expensive shutdowns is to develop systems that can run at a very low load. The boiler needs to be capable of being fired at a low rate while maintaining flame stability. So mill and burner redesigns are allowing the conventionally accepted 40% minimum firing rate to be improved upon a lot. This makes it possible through changes to mill sizes with new burners to achieve a 25% load on 2 mills. This is shown in this diagram here. In some tangential corner-fired systems, the minimum load has been further reduced by operating a single mill to give turn down to less than 20% or even only 15%, as shown, for example, at the subcritical 220 megawatt Heilbronn Unit 7 in Germany, which opened in 1985. Use of tilting burners will also help to reduce the need for reheat attemperation at partial load. Incidentally, it is even possible to go further by modifying the pulverized coal feeding arrangements to incorporate hoppers for temporary storage of the milled coal. Even lower burning rates become possible. The next area of plant that I will look at embraces the pressure parts of the boiler, including tubes, headers, and membrane walls. Conventionally, when baseload operation was the norm, creep was the main deterioration mechanism to take account of in designing these large, stressed components for sufficient length of service. But when plant cycling is more important, life consumption mechanisms become determined more by fatigue and fatigue interactions with creep and corrosion. And thermal expansion can also cause damage, not only to process components, but also to ties. So the main issues here are potential damage from stress variations. The key to solving this is to reduce the thermal gradients that will develop when the load changes, so that the changes in stresses on the components are less severe. 3 examples of how to achieve this are listed here. First, using new, stronger steels to allow reduced metal thicknesses, accompanied by using a different approach to determining the necessary component wall thicknesses that gives more weight to creep fatigue, as opposed to creep alone. This is shown in the next slide. Other ways include increasing the number of headers or installing external steam heating or hot storage systems. These allow components to be kept closer to operating conditions during short-term shutdowns. Lower minimum loads can be enabled by incorporating design features, such as internally rifled tubing to permit reduced fluid flow rates without metal overheating, or by adding economizer or feed water heater bypasses. Excuse me. For the turbine, again, major issues are damage from stress variations. The high temperature and pressure conditions of supercritical and ultra-supercritical turbines necessitate the use of thick-walled components so that they possess adequate strength. But this can limit the rate of temperature change consistent with keeping thermal fatigue to acceptable levels. One of the difficulties is the challenge of maintaining very small clearances between stationary and moving components that can threaten rubbing or excessive losses during output changes. The measures on this slide are all about reducing the stresses. One way is controlling the rate of temperature swing in the outer casing by steam cooling, such that its temperature is 30 to 40 degrees C lower than that of the inner casing at the corresponding position along the turbine during load changes. This also allows the thickness of the outer casing to be reduced. Although throttling has been used traditionally to vary output from a turbine while keeping the pressure constant, sliding pressure operation has become a commonly applied method in supercritical systems. It makes matching steam and metal temperatures easier and maintains higher temperatures during shutdown. Turbine bypass systems are a virtual necessity in plants designed for on-off and other flexible forms of operation. They allow all or part of the steam to bypass the high pressure or low pressure turbine so that the rate of temperature change in the turbine can be managed as the boiler is starting up and shutting down. Advanced sealing and other measures to maintain correct clearances and startup can be fitted during retrofits. This slide shows a conventional shaft labyrinth seal and an advanced seal using sprung segmented sections. Other systems include spray abradable soft coatings and brush seals. Methods available for primary frequency control include the well-established means of opening of throttled main steam valves, but also nowadays condensate throttling, feed water heater bypass, and HP stage bypass are also available. In condensate throttling, the turbine control system opens the governor valves to utilize the reserve steam storage capacity of the boiler, as in conventional throttling, but the flow of condensate to the low-pressure feed water heaters is reduced at the same time. The flows of extraction steam are thus reduced, leaving additional steam flow in the turbine. Maximum output can be reached after about 30 seconds. Provision of feed water heater bypasses is another means to increase flexibility. It can actually help with reducing minimum load by allowing a reduced final feed water temperature, but it may also, in contrast, be designed to give a power boost. Use of high-pressure feed water heater bypass can produce additional power for about 20 to 30 minutes by allowing more steam through the turbine. HP stage bypass permits additional HP steam to be admitted to the high-pressure turbine some stages after the first blade row, when the bypass valve is opened. The system is normally designed to give a short-term 5% increase in power, but it can be designed for more. Normal operation at 100% MCR is achieved with the stage bypass valve closed. HP stage bypass is the most efficient means that is available for achieving rapid load increases of 1% per second, because throttling losses are at a minimum, as it uses full arc admission. Even more flexibility than this can be achieved by installing storage systems for the low pressure or high pressure feed water. A simple example is shown here from GE using a storage tank incorporating hot and cold water, with displacement of each by the other during the increased or decreased power requirements. A more complex variant uses additional feed water heaters. Emissions control systems also, of course, need to be able to cope with load swings, low loads and shutdowns while preserving their effectiveness. Here, the SCR, Selective Catalytic Reduction for NOx control, Electrostatic Precipitator, or ESP for particulate control, and Flue Gas Desulfurization, FGD, for SOx control are shown. I'll start with the particulate control systems. These can usually cope with a plant operating at partial load and rapid load changes without problems. Inlet gas temperatures need, however, to be watched. They must not fall so low that acidic moisture condenses on particles, causing adherence of solids to bag filters, or a resistivity that is too low for efficient ESP performance. For SCR, for NOx control, to avoid problems with ammonium bisulfate formation, the conventional solution is to add a flue gas or water-side economizer bypass to enable the flue gas temperature at low load to be kept at the design value. Other options include closer monitoring of conditions and modifying the inlet temperature distribution using baffles. Whatever method is used, provided the correct temperature can be maintained, rapid rates of load change can generally be accommodated with retention of performance. For FGD, it can be possible to obtain savings in energy consumption at part load by updating the control systems and switching off some circulation pumps. The number of shutdowns and startups needs to be minimized to avoid slurry solidification and accumulation of startup fuel oil residues on linings, quite apart from averting long warm-up periods. Keeping within required emissions limits during rapid load changes requires sophisticated control, and an increased liquid-to-gas ratio may be needed. It is generally worthwhile replacing control and instrumentation systems in older plant to increase efficiency and flexibility. Sophisticated control and instrumentation will also improve minimum load capability, for example, through additional flame monitoring. RWE has carried out control system retrofits on its 300 megawatt and 600 megawatt lignite-fired units, and this has achieved greatly increased ramp rates and lower minimum loads, as you can just see in the figure here. Boiler and steam systems responses are significantly different at low load from those close to normal output. The effect becomes greater when deterioration as a plant ages comes into play as well. This can affect the response of the boiler, and control performance becomes degraded and flexibility suffers. Installing modern systems can stabilize such non-stable loops. Modern monitoring and control systems also keep steam temperatures and clearances in the turbine under better control during startup and load changes. In a promising development area, self-learning predictive systems will coordinate all a plant's main systems and so optimize the whole plant. This should be highly beneficial in realizing greater flexibility through reducing stresses on plant components while maximizing efficiency and maintaining minimum emissions. And while, as shown here, modern control can enable combining the operation of multiple units, remote monitoring and coordination of all major units is a possibility for the future, for maximizing overall availability and flexibility of supply to grids. Not all coal-fired power plants use pulverized coal combustion, of course. CFBC, circulating fluidized bed combustion, has a significant share of the market, while integrated gasification combined cycles are slowly being deployed, and very high temperature pulverized coal, known as advanced ultra-supercritical or AUSC plants, are also in development. Coal-fired carbon capture and storage plants are also in prospect for the future. The next few slides then consider the flexibility properties of some of these technologies. I'll start with CFBC. CFBC combustion takes place at lower temperatures than in pulverized coal systems in a highly mobile bed of ash and fuel. Most of the solids are continuously blown out, then recirculated to the combustor, and heat is extracted for steam production from various parts of the system. The refractory linings used to protect the water walls of the combustion chamber can limit minimum load without supplementary fuel. Refractory damage has to be avoided, and in any case, bed temperature needs to remain within the design range. Wide or rapid temperature changes during startup, shutdown, or load following can cause damage in both combustor and loop seal areas. Nevertheless, a number of units have been cycled for some years. Foster Wheeler offer for their compact CFBC boilers a reheat steam bypass system for reheat steam temperature control during startup and shutdown. Load following capabilities can be similar to those of pulverized coal units. Part loads down to 25% of MCR and load change rates of up to 7% per minute can be possible. Now looking at IGCC. This uses a combination of gas and steam turbines to generate electricity. It's like a natural gas-fired combined cycle plant, but with a front-end coal gasifier and gas cleanup. The air separation unit, the ASU, oxygen plant, can use air extracted from the gas turbine or separate motor-driven compressors, or both. High degrees of integration favour higher efficiencies, but the greater complexity slows startup as the various processes have to be brought on stream in sequence. So the ramp rate will basically be determined by the gasifier and ASU ramp rates, and is typically about 3 to 5% per minute, which makes it similar to many older PCC units. The minimum load is generally 40 to 50%, and this is determined by the achievable minimum outputs of the entrained flow gasifier and the ASU. If 2 gas turbines are installed, this gives more flexibility, as excess syngas would be stored at times of low load, then fed to the turbine at times of high demand. Oversizing the ASU to allow liquid oxygen and nitrogen storage is a potential means of increasing load range. At low demand, for example, excess power would be used by the ASU. IGCC plants can also be designed for polygeneration, so varying the balance of products, including electricity, liquids, and synthetic natural gas as power demand changes. Conceptual designs include use of electrolysis to consume excess power from the plant or the grid to provide additional hydrogen for methanation of the syngas to SNG. Now we'll look at CO2 capture and storage plants. Even where carbon emissions prices become significant, future CO2 capture plants should be able to operate at higher capacity factors than plants without CO2 capture because of requiring fewer emissions allowances to be used. A proportion of these then may provide baseload, but some may need to operate flexibly, as wind and solar energy plants are likely to operate ahead of them. Studies are providing indications of how flexible operation of coal-fired CO2 capture plants could be realized. There are 3 main types of CO2 capture system: post-combustion capture, oxy-fuel combustion, and pre-combustion capture. I'll briefly describe them all. In post-combustion capture, usually an aqueous amine such as MEA is used to absorb the CO2 from the flue gas. The rich amine is then regenerated by heating to around 120 degrees C, and the liberated carbon dioxide is compressed and stored or utilized. A rapid increase in output could be achieved by temporarily diverting the flue gas away from the capture unit. As in use, this consumes considerable energy. Steam to the solvent regenerators would be turned off, increasing flow to the low-pressure cylinders. At times of normal and low electricity demand, the unit would be reconnected to the CO2 absorber. Large vessels for storage of CO2-laden solvent would be needed if long periods of peak load were to be satisfied. The solvent would be regenerated at times of low power demand, and steam would be diverted to the regenerator, thus achieving lower than normal minimum loads. The steam cycle would need to be designed to accept the resultant higher flow. It is possible that ramping could be better than for a plant without capture. The large quantity of solvent that would have to be stored would mean that operating at peak output for long periods of time would not be attractive. In oxy-fuel combustion, the coal is combusted in oxygen, which is produced in an air separation unit. The emerging flue gases then consist largely of CO2. and a stream of CO2 is taken off for purification, compression and storage. The remainder of the flue gases is recycled to the combustor to control the temperature. Flexibility could be achieved through providing large-scale oxygen storage, as oxygen production uses considerable energy, so the gas would be produced and then stored when electricity demand was low. The stored oxygen would then be used at periods of high power demand, with the air separation unit then used less. In IGCC, pre-combustion, CO2 capture plants will use the water-gas shift reactions to convert the syngas, which contains carbon monoxide, to carbon dioxide and hydrogen. The CO2 will then be removed by physical or chemical scrubbing. The hydrogen will finally be fired in the gas turbine. So for flexing, the systems could be designed to allow hydrogen to be stored for firing in the turbine later. Combined cycle or open cycle hydrogen-fired gas turbines could be used, further increasing flexibility. Gasification and CO2 capture would operate at base load, so avoiding difficulties of flexible operation and reducing costs. However, variable load operation of hydrogen gas turbines would need to be confirmed. Other methods would divert excess power to the oxygen producing plant, reducing net plant output, and store the gas for use when demand is high. Akin to that described earlier for non-capture IGCC plants, or co-production of synthetic natural gas, which could be stored in the natural gas grid. So then, in summary, the main requirements are capabilities for rapid startup, fast load following, and increased grid frequency stabilization because of the decreasing stability of the grid as the synchronous plants become a smaller proportion of total capacity. The means for achieving these have been outlined in this presentation. We've shown that most plant areas are affected. The potential life-limiting effects of plant cycling are known, and new systems give high flexibility with good plant life and thermal efficiency. CFBC plants can have a reasonable degree of turndown, subject to limitations imposed by the need to maintain bed fluidization and preserve boiler refractories. IGCC plants could have flexibility improved by a variety of means, including exploiting the energy storage potential of the latter. And then for CO2 capture plants, there are a number of possible ways of achieving flexibility which could potentially be available. And I've just gone over the details of these very briefly. So finally, I'd like to thank you very much for listening. The information I've presented here is based on a number of reports that we've published here at the IEA Clean Coal Centre, which are available to download from our website after you've registered. We've produced reports, for example, on all the methods of CO2 capture, on CFBC, on IGCC, and on flexibility itself. A colleague of mine, Maggie, is also working on flexibility, and she'll present her work next year. Finally, I'd like to say if you do have any questions about this presentation or would like clarification, please drop me an email, which you can see on this last slide, and I'll respond shortly. And finally, before we go, I'd like to highlight that the next webinar from the IEA Clean Coal Centre will be presented by Dr. Ian Barnes on Wednesday the 17th of October. And it's going to be an interesting one on high-efficiency, low-emission technologies and outreach work that's going on in Japan and South Korea. So thank you very much for listening, and goodbye.